Welcome to the class, Tatu.
Sir.
We're going to start in a couple of minutes. I'm going to be back in like 3 minutes.
Yes, sir.
What you can do, you can look at the test, the subjects, the test you're writing on Tuesday, or you can get your stuff together that you want questions on. I'm going to be back in a minute.
Yes, sir.
Right, I'm back. Okay, so you are aware of a test you're writing on Tuesday?
Sir?
I think there's a test you're writing on Tuesday. Is that right?
Yeah, yes, sir.
Okay. Have you looked at it?
No.
Okay. All right. We're just waiting for Bianca.
Yes, sir.
Welcome to the class, Bianca. Please, can you now hear me, Bianca? I can see your mic's moving, but I can't hear you. There we go. Speak again, Bianca.
Okay. Can you hear me, sir?
Right. I just told Tatu that there's apparently a test on Tuesday.
Okay.
Okay. Yes or okay or no?
Sure, I didn't know that, but thank you for telling me.
All right. Good. And it's apparently on intermolecular forces.
Okay.
So that whole chapter on chemical bonding. So it's ionic bonding, covalent bonding, metal bonding, and then we're going to then they're going to ask stuff on electronegativity and also on molecule polar or non-polar, and also your van der Waals forces.
Okay.
I think we've done something on this. Is this correct?
Yes, sir. I think we have.
Okay. Right. So what are we doing today? We can
last week, sir, you said you're gonna start on like straight your non-metry.
Okay. You need to make a quick decision. Are we going to continue with that, or are you going to do revision on intermolecular forces? Doesn't matter.
I'd like to do revision, sir.
Okay. And Bianca?
Yes, sir. Can we please do revision?
Okay. So the chapter is chemical bonding. And we've basically done this. I'm just going to scroll through. There's our periodic table. We've explained when a molecule is polar or non-polar. We've looked at the various molecules, and this is also polarity. And then we've looked at 4 different van der Waals forces, and also ion dipole and ion induced dipole forces. Okay, so we've looked at reasons why some or other liquid has a higher boiling point than another one, comparing the same intermolecular force and also comparing different intermolecular forces. We've done it here. And this ion dipole I've explained, and we've also looked at dative covalent bonding. So we're just going to redo it. Okay, so chemical bonding. Now, what I'm going to do now, we don't have enough time to go through the whole chapter. There's a section we have a graph that basically looks like this. That section we're not going to do. You have to study that.
Yes, sir.
Okay, so what are we going to do today? We're going to look at Lewis diagrams or Cooper diagrams, because these diagrams are going to show you some, if there's any bonds that's between the atoms. It's called intramolecular bonds. If they are polar or non-polar. And then the next thing, we're going to look at the molecule. If the molecule is polar or non-polar. And then we're going to look at the van der Waals forces. And this is going to determine our physical properties, like boiling point, vapor pressure, viscosity, etc. So we're just going to run through the chapter again. Oh, I am going to include VSEPR, not W, VSEPR. It's PR, it's not R in English. PR structures today. It's taken out of the CAP syllabus for the next 3 years. So strictly speaking, you're not allowed to be asked to give those names. But maybe you get it because it's in your textbook. So I'm just going to make sure that we also cover VSEPR models. Right. So what I want you to do, take out a paper or a book and a pencil. And you have to have a periodic table with you. Those 3 things. Just take 5 seconds, get those 3 things together. Paper, pen or pencil, maybe calculator if you want to. You're not going to need it. And your periodic table. I can't go back to the periodic table all the time. Okay, cool. Let's start. I just need to get something here so that I can actually copy and paste stuff for you if you need it. So let me get my stuff together. So make sure that I get all the, some of the 3D models are quite helpful. Okay, so it's that one. Good, let's start. Right, okay, first thing. I want you to draw Lewis and Cooper diagrams of the following: water, H2O, ammonia, NH3, methane, CH4, and also carbon dioxide. Just those 4. Let's quickly draw Lewis and Cooper diagrams of those. So if you've got your textbook with you, they should be in there because they are some of the most popular ones. Right. I actually want to replace CO2. I just want to replace it with something like chlorine gas for now. Right. Water, I'm going to draw a Cooper diagram. Water looks like that. Is that correct? In a Cooper diagram?
Yes, sir.
Good. Okay. In other words, basically, I'm going to draw the Cooper diagram, just replacing the double bonds with a line. So that's a Cooper diagram. The Lewis diagram would have just looked like this.
Yes, sir.
Good. Are you with me, Tatu?
Yes, sir.
Because I'm not going to draw a lot of stuff. I'm just going to draw Cooper diagrams because we just want to see what the molecule looks like. Okay. And ammonia is NH. And then there's 1 pair of lone electrons. Good. CH4, methane, looks like that. And chlorine gas just looks like that. Okay, now I want you to look at the molecule and tell me if any of the bonds are polar or non-polar. So look at these bonds. I'm going to highlight this bond here. Is that bond polar or non-polar? So the bond in each one of those. I'm going to make the screen slightly smaller and move it to the side. Can't move it to the side, so I'll move these. Right, so any of those bonds, the bond between the oxygen and hydrogen, is it polar or non-polar? It's polar. It's polar covalent. Why is it polar?
Because the electron negativity, so it is higher than
Because the change in electron negativity is what?
it's higher than like
Higher than 0.4
1.
or 0.3.
Oh, isn't it 0.9, sir?
No, no. If it's higher than 0.9, it is it's also polar covalent, but it's strong polar covalent. Basically, is there a difference between electronegativity? Yes, there is a difference. Oxygen is what? Is it 3.5? 3.0.
Yes, it's 2.5.
So it's 3.5. Oops, not 3.3. It's 3.5 minus 2.1. So I'm just going to not do that calculation. It's 1.4, isn't it?
Yes, sir, 1.4.
The difference in electronegativity is 1.4. So it's polar covalent with a T at the end.
Okay.
Right. What about the molecule? Is the molecule polar or non-polar? The molecule is also polar. And why? Why is the molecule polar?
So because both of the atoms that are being used are
It's about the distribution of charge, basically. So what happens is all the electrons are drawn towards the oxygen side of the molecule, making that oxygen negative and the hydrogen parts positive. So there's an unequal distribution of electrons. And due to the asymmetrical shape of the molecule, it is polar. So the electrons are what? Distributed what?
unequally.
Unequally. I'm just going to write shorthand. And so what?
Oh, and like they're not symmetrical.
Yeah.
Oh,
The molecule is not symmetrical. Asymmetric. It's a Y.
but sir,
Yes.
I don't get why it's not asymmetrical, because if you cut like from like the oxygen side, you're gonna get like
Like I cut it now.
yes,
Okay, you're right. Then it's symmetrical. But if I cut it like that, it's not symmetrical.
okay, sir.
So you can take the middle of the molecule and you cut it with a cross. The top and the bottom and the left and the right should look the same. If it doesn't,
So
it's not.
sir, the Lewis diagram, do you have to draw it exactly like that?
It's the correct one, yeah. Even if you draw it at a 90-degree angle, it's not symmetrical. That angle there is 104.9 degrees. Okay, cool. Can anyone give me the VSEPR code and name? That is it angular?
So
Yes, sir.
yeah.
Okay, it's angular. And the code, please? A is for the central atom. So oxygen.
Okay.
AXE. So X is for either the atoms bonded to the central atom, and there are two, and E for the amount of lone pair electrons. There are two.
Okay.
Good. Okay. Right. I don't want to waste too much time here. Let's quickly do the others. So, are any of the bonds in my ammonia polar? Yes, they are polar covalent. Why? There's a difference in electronegativity between nitrogen and hydrogen, you can work it out. It's 3 minus 2 comma 1, so it's 0,9. So it's actually strong polar covalent. Difference in electronegativity equals whatever. Is the molecule polar or non-polar? Polar.
It is polar, yes, sir.
Okay. Same reason as the bottom one. Okay.
Yeah.
VSEPR.
It would
It is
be.
angular.
No.
It is not angular.
No. Is
Is
it not?
it trigonal? What?
Trigonal.
Trigonal, sorry.
Trigonal pi. How do you spell that? Pi.
P-L-A-N.
Yeah, it's wrong.
No,
That's why I
sir.
can't finish it. I spelled it wrong.
P-L-A-N-A-R.
Like that. P-Y.
Yes, sir.
P-Y-R-A-M-I-D-A-L. It means basically the following. It's a triangle at the bottom. And it's built as a pyramid.
Pyramid.
Yeah.
Yes, sir.
So it's a triangle at the bottom, but the form is like a pyramid. I wish I had these structures now. You should have them in a book. Okay, good. And then AXE, AX3E1.
Mm-hmm.
Good. Methane gas. Any of the bonds polar? Yeah, polar, covalent. I just took the electronegativity between carbon and hydrogen. And I got a value of something like 0,4. So it's polar. Is the molecule polar? Look at that whole molecule. Is it polar or non-polar? It is
Non-polar.
non-polar. Why?
Because
The electrons are
Yeah.
the electrons are equally distributed
distributed.
over the whole molecule, no? And the molecule is
sir.
symmetric, or symmetrical in shape. Good. What about the VSEPR name and code? The name is what?
It is
Tetrahedral.
Yeah.
Tetrahedral. And it's AX4.
E1. Oh,
E0, no E's.
okay.
You don't have to write the
so
E.
what does the A stand for?
The A is just indicating that there's a central atom.
Okay.
Oh.
X.
X is the amount of atoms bonded to the central unit. 1, 2, 3, 4. Or you can think of the pairs of shared electrons bonded, but it's going to be the same as the amount of atoms. And then E is the amount of lone pair electrons. There are none. And then chlorine gas is, what about these bonds? The bonds are non-polar. Because the difference in electronegativity is 0. Just give me a second. Some other reason I'm running low on battery. There we go. Good, fixed it. Right, so look at these chlorine atoms. They are bonded non-polar because there's no difference in between the electronegativity of the two. What about the molecule? Well, the molecule will be also non-polar. Is that correct? Yes. Shape?
Yes, sir.
Linear.
Yeah, it's linear.
That's an R then.
Mhm.
And there is no AXE.
What is it?
It doesn't have a code because it doesn't have a central atom.
Okay.
We don't give it a code.
Okay.
Good. Okay, so we've done this.
Yes, sir.
We've looked at the molecules, if they're polar or non-polar. We've looked at bonds, if they're polar or non-polar. Then we're going to move on to van der Waals forces. So now I'm going to look at not the forces between the atoms, but forces between two different molecules. So this can be sometimes tricky because all they're going to do is something like this. They're going to say, okay, I'm giving you, let's go back to methane, CH4. And they're going to ask you, what intermolecular force is there? And because they only show you that one molecule, you sometimes do forget that they're actually referring to the force between various CH4 molecules. Right, so we're going to look at the 4 van der Waals forces. Which one of Waals force is between those two molecules?
Sorry?
Which van der Waals force, which intermolecular force is between the two methane molecules? Remember, there's hydrogen bonding, there's dipole-dipole, there's dipole-induced dipole, and there's also London forces. Then we have iron dipole and iron-induced dipole. So if you have a non-polar molecule and another non-polar molecule, the intermolecular force is London forces. You can also call it dispersion forces, or you can call it induced dipole forces. But London is quickest, easiest. Do you understand what to do? Okay, cool.
Yes,
So
sir.
I'm not going to test you on this. So I'm going to have hydrogen fluoride. I'm going to have what? BF3. Then I'm going to have what? Let's say CCl4. Right. I want to know which of these three. Okay, name the intermolecular force between the molecules in hydrogen fluoride. In other words, I'm asking, what is the force between two different hydrogen fluoride molecules?
Wouldn't it be hydrogen bonds?
Very good. Hydrogen bonding.
Yes, sir.
Hydrogen bonding is a specific dipole-dipole force when hydrogen is bonded to fluorine or oxygen or nitrogen.
So only those three.
Only those three.
If it's something else, then it's a completely different bond.
Yeah, if I had hydrogen iodide
Yeah.
and another hydrogen iodide, this would have just been a polar molecule and another polar molecule, which would have been dipole-dipole.
Okay.
Are you with me, Tatu?
So,
Okay, we'll answer questions on that in a minute. Okay, BF3, difficult molecule.
isn't it a thing?
I'm going to quickly draw a
Dipole.
Yes, sir. Wouldn't it be a dipole-dipole force?
Okay, I'm asking, is this molecule polar or non-polar? That's what a first question. Well, the molecule is symmetrically shaped. Therefore, the electrons will be dispersed evenly. So it will be non-polar. So this is non-polar, and this is non-polar. So this is London forces. Remember, boron is a what? Exception to the octet rule. Boron is in group 3. It can only accommodate 3 valence electrons, only has 3 valence electrons, so it can only have 3 bond areas. 1, 2, 3. So that's the only way it can bond. There's no electrons that are not bonded to any atom. So those angles between the fluorine atoms are exactly the same, 120 degrees. There isn't any lone pair of electrons.
Okay.
Good, that's a difficult one. And then CCl4 looks exactly like your CH4 molecule. So it's also non-polar. And another CL4 is also non-polar. So it's again London forces.
Mhm.
Right. Okay, we'll do one or two more, and then we're going to do questions. So I've got, say for instance, I've got the following. Sodium ions in solution. Then I have, what else is quite popular? Okay, let's do carbon dioxide, yeah? And let's do what? I don't know. Quickly think about those two already. I'm just going to find one more. Oh, that one is done. That one is done. PCl5. Phosphor pentachloride. Now, I want to know,
Oh.
between those molecules, which are the forces? The first one is the difficult one. It's the problematic one. So if you don't know that one, skip and try think of the other two. Come. Anyone?
So would the CO2 be a dipole force?
Right, let's draw that molecule. Carbon, double bonded to an oxygen, double bonded to an oxygen, and another carbon, double bonded to an oxygen, double bonded to an oxygen. This is non-polar.
So would it be a London force?
Oh, very good. London. PCl5 is difficult to draw on a flat surface. So that one is symmetrically shaped. So this is also non-polar and non-polar, the other one. So this is also London.
So it would be a London.
Okay, and this one is a sodium ion that's bonded to a water molecule. That AQ means in solution. So this gives me ion dipole forces. Good. Okay, now the questions that are a lot of marks are as follow. I'm just going to try and get you a proper question quickly. I've got it in Afrikaans, so we'll just translate. Okay, I've got iodine gas. In other words, there's two iodide molecules, and there's another one. And then I've got bromine gas. Now, which one of these two will have the highest boiling point? And give me a reason. Let's try and get the intermolecular forces first.
Okay.
Quick, what are these forces between these iodine molecules? Is this polar or non-polar?
Non-polar.
So what are the bond between two non-polar molecules?
The London forces.
Yeah. And this bromine, is this bromine molecule?
Yes, London forces, sir.
Okay, cool. All right, let's start. Let's ask the question. I want to know first, which molecule or which substance, which one, bromine, iodine gas, or bromine gas, has the highest boiling point, plus give me a reason, and that will be 4 marks. So 1 mark for the answer. Which one has the highest boiling point? 1 mark for the answer.
The highest boiling point,
Yes.
it'll be the bromide. Sulfur.
No, it will be the iodine. I2. Okay, let me answer these in blue so I get the answer quicker. The answer is that one. 1 mark. The reason is why. Okay, you have to include in your answer the type of intermolecular force. You have to include energy in your answer. And you have to give the reason. So type of intermolecular force, 1 mark. Okay, the answer, 1 mark. Type of intermolecular force, 1 mark. Energy, 1 mark. And then the reason, because of that, a 4th mark. So there's 1 mark for iodine gas. And then you're going to answer it as follows. The intermolecular force between both molecules is what? Is London forces.
Yes.
Okay, and for that you get a mark. Why am I not writing neatly? That's 1 mark. Then, okay, what is the difference then between? The iodine has a higher molecular mass. What does that mean? It basically means that there's more electrons, which means there are more electrons causing, you can either use the term a bigger dipole moment, but that's not in your textbook, so I don't recommend that, causing more polarity. What does that mean? Okay, I'll explain that now when you go back to it. Causing more polarity. Therefore, more energy is required to overcome the forces. Therefore, there's a higher boiling point. 1, 2, 3, 4 marks. I won't say, sorry, let's not do forces here. Let's say bonds. Because overcoming the bonds means it becomes a gas. So the higher molecular mass means that iodine's got more electrons around each of those atoms than bromine. More electrons means that there are more electrons that can move to the one side of the molecule, causing a bigger polarity. A bigger polarity means that those 2 iodine molecules will attract one another stronger than the bromine. Iodine has got 53 electrons and bromine only has 35. So there's 53 electrons times 2 that can move around in this part of the iodine molecule. There's a lot of electrons that can move to the one side of the molecule, causing a momentary dipole or a molecule that's polar for a while. So there's more electrons that can move to one side. This positive side becomes strong and this negative side becomes negatively strong. That means it attracts the bottom molecule quicker and easier and stronger. While bromine has got less electrons that can polarize the molecule. And that's because it has a lower molecular mass. This is very important. Right. Another one. Okay, what we've done here, we have compared a physical property like boiling point with 2 molecules that has exactly the same intermolecular force. Now we're going to compare a physical property with molecules that have different intermolecular forces. So they're going to ask something like this. Okay, we've looked at, very important, we've looked at molecular mass as the answer. So now they're going to give you this, pH 3. and they're going to give you NH3. So I want you to draw Lewis diagrams for both of those. Do the ammonia one first if you're struggling. Tell me when you're finished. Okay, so I'm going to draw the ammonia first as well. Ammonia is in group 5. It's got 5 valence electrons. So there's one bond. I'm going to draw a Cooper diagram again. Did you draw Cooper or Lewis? Okay, let's draw the Lewis diagram next to it. There we go. And pH 3 is difficult. Oh, once you've drawn the ammonia one, pH, they're both in the same group. Looks like that. The Lewis diagram would look exactly the same. Good. Okay, now, question, 4 marks. Which molecule or which substance, I'm not going to look at the molecule, which substance has the highest vapor pressure? Vapor pressure. What does vapor pressure mean? It's the pressure of evaporation, or the pressure caused by evaporation. So the one that evaporates the quickest will have the highest vapor pressure. So the one that evaporates the quickest is the one with a weaker intermolecular force. So I want to know basically which one has the weaker.
So wouldn't it be the NH3?
Okay, let's look at the intermolecular bonds. So we have pH 3 bonded to another pH 3. And in this other one, we have NH3 bonded to another NH3. Okay. Is this molecule polar or non-polar?
Polar.
Yeah, there's actually a huge, not debate on that. There's actually, there are different memos have different opinions about it. Some say it's non-polar. Okay, it is polar. You're correct. Why? So some memos thinks it's non-polar because the difference in electronegativity between phosphor and hydrogen is what? Look in the
0.9.
periodic table. It's 0. Can you see that?
Oh yeah, 0.
Yeah. But that lone pair of electrons there causes the what? The hydrogens to bend down, and it makes the one side of the molecule slightly polar. So for me, it's polar. So that is dipole-dipole. Okay, what about this molecule?
It's dipole, so or
No.
polar.
It's not, it's polar, but it's not dipole-dipole.
Polar.
What is it?
So it wouldn't be
Hydrogen bonding. How do I know that? Well, there's hydrogen connected to nitrogen. It makes that bond, that specific dipole-dipole bond called, it makes it stronger than a normal dipole-dipole bond. It's called hydrogen bonding. Good. Which one is the stronger intermolecular force? Dipole-dipole or hydrogen?
Um, Yeah, what did it be?
Hydrogen bonding is stronger. So the pH 3 has the weaker bond. And therefore it is the higher vapor pressure. It will evaporate quicker. So this is a way to answer it. Which one has the highest vapor pressure? And the first mark is pH 3. It's called, this is phosphor hydride. Just want to make sure about that word, because there's a specific word they use for that. Phosphine. You don't have to know this word. You don't have to know it, so let's just ignore it. So phosphine has got higher vapor pressure. Why? Another mark. Now the reason comes in. I'm going to name both intermolecular forces. pH 3 has what? Dipole forces. While, so my pen is not going to be with me now. While the NH3 has hydrogen bonding. Okay, that's one mark because you've given both intermolecular forces. Then you must see an energy component or a strength component. The hydrogen bonding, I'm just going to do shorthand, is greater or is higher strength, is stronger than the dipole bond. Therefore, more energy, big E's energy, is required. Or you can say less. Maybe it's better to answer towards in a way that amplifies our answer. Therefore, less energy is required to overcome the pH 3 bonds. Or you could have said more energy is required to overcome the bonds between ammonia. And last, therefore, the pH 3 will evaporate quicker. At the same temperature. Boom. Boom. 4 marks. Because this is very important for the test. Because apparently your test is going to be 50 marks on intermolecular forces only, which is a lot of marks actually on that one chapter. That means you're going to basically get everything.
Okay.
Good. Another page. One other thing we have to do. I want to know if I give you this molecule, which is called ammonium. What type of bond? What type of bonding occurs?
Isn't it dative covalent
Very
bonding?
good. So in our ammonia and in our hydronia molecules, what happens is we've got the first one, we have ammonia, NH, with one lone pair of electrons. Then I have a hydrogen ion that's attracted to that molecule. Why? This lone pair of electrons is negative, and that hydrogen ion is attracted to that. But hydrogen doesn't have any electrons, that hydrogen ion. So basically its one s orbital is empty. So it's nice because 2 electrons can fit into that one s orbital. So in this case, ammonia will supply both electrons to bond in that bond. And my hydrogen will go and sit there. And this whole molecule will have a positive 1 charge. That's called dative covalent bonding. It's very important for the test. Just give me a second. Sorry, I can't. I think you spell it like this: dative covalent bonding. Just check that.
No, so it doesn't have an I, just
Oh, without the
translate
I.
Yes, sir.
So it's not dative, it's just dative. Dative covalent bonding. And the hydronium molecule does exactly the same. It's just water molecule that attaches to one of those, or one hydrogen ion attaches to that to the one of the lone pair of electrons on the water molecule. Right. Okay, cool. A question for you, just quick to check if you've learned what we've done. I have hydrogen fluoride, and I have hydrogen iodide. This is a tricky one. Then they're going to say, look, the hydrogen iodide has a higher molecular mass. What do you expect? It must have a higher boiling point. No, we've just done that. The higher the molecular mass, the higher boiling. It has a higher molecular mass than the hydrogen fluoride. But the hydrogen fluoride has a boiling point of, I think it's going to be something like, it's 113 degrees Celsius. And the hydrogen iodide has a boiling point of 83 degrees Celsius. These are just numbers I'm guessing. I can't get the specific value. Why is it now that the hydrogen iodide has a lower boiling point? It has a higher molecular mass. Write that down. I'm going to get those values for you, proper values. And I want you to figure out, why is this one now, even though the molecular mass of hydrogen iodide is higher, why does it have a lower boiling point? Oh, damn. It is actually minus 35 degrees Celsius. I can't believe that. Anyway, so there's negative 35 degrees Celsius. It's actually a very low boiling point. Let's look at hydrogen fluoride. It should be higher. Oh, this is 19 degrees Celsius. So it is still much higher. Why is the hydrogen fluoride, why does it have a higher boiling point than the hydrogen iodide? This one has a higher molecular mass. Figure it out. Give you 2 minutes.
So
Yes.
I think it's because there is no like the difference in electronegativity is like very low, it's like to the negatives.
The difference in electronegativity doesn't affect the physical properties. Remember, when it comes to physical properties like boiling point, vapor pressure, and viscosity, we are thinking about this force, the intermolecular force. The difference in electronegativity is concerned with the intramolecular force. There's your electronegativity difference. We are looking at these forces. And if they are the same, then we're looking at the molecular mass. So we need to compare these two intermolecular forces. And if they're the same, then it's only the molecular mass that we have to look at. So those two forces will be different. Answer. What is the intermolecular force between hydrogen fluoride and another hydrogen fluoride molecule?
I think it's polar covalent.
No, no. You're thinking about this force. You're thinking about
Sorry,
the
sir.
between the two. That is correct. The force between the hydrogen and the fluoride is polar covalent, but that's not an intermolecular force, and that's not the force that is determining the physical properties. This is called hydrogen bonding. Why? It's because there's hydrogen and fluoride in a molecule. If there's hydrogen connected to either nitrogen or oxygen or fluorine, what then? Then we have hydrogen bonding. It's a special type of dipole-dipole force. This one is just two polar molecules. So it's dipole. And hydrogen bonding is a higher, it's got more, the intermolecular force, hydrogen bonding is a stronger intermolecular force. So you'll need more energy to overcome those bonds. And therefore, hydrogen fluoride will have a higher boiling point compared to hydrogen iodide. Good. Okay. So let's look at strategy. You'll have to learn all your definitions. You'll have to read through the chapter very carefully so you get all the points, all the small multiple choice stuff that comes out of the theory. Then because those calculations really. Then you have to look at possible answer questions. So you'll have to look at a past paper or 3 to see what type of questions they ask. And then you have to do it. Do the paper. Get the memo. Don't do any paper if you don't have a memo. If you don't have a memo, it's not good. Get the memo and the paper.
Okay.
Okay. Look, there's a couple of minutes left, so we're not finished yet. Just want to make sure that I can give you a paper. Let's see what I've got here. This is this is for instance, this is Afrikaans. I've got Afrikaans IAB papers, which is quite interesting. Okay, so we can't use that. Anyway, IAB paper is probably not the best anyway because you're on CAP syllabus. Where do you find papers?
So,
Hmm?
I don't know where to find them.
You type in grade 11 physical science past papers, or just past papers, grade 11 physical science. And then you'll get lots of the normal department papers that you can use. Let me get one. I only have paper 2, yeah. So I'm going to just pull out a question out of a paper just to show you what it can look like. It's not difficult because you're only writing on one specific topic. You're not doing energy, not doing gases. Yeah.
I'm getting exam question papers, sir.
Yeah, exam questions is what you want.
So paper 2, right?
But just make sure you've got a memo as well.
Yes, sir. So paper 2.
Yeah, I'm listening. I can't hear you, Tatu.
I'm like paper 2, sir. Like that's the one where chemistry. That's the
Yeah,
chemistry
paper 2 is the
paper, right?
chemistry one. This is like a just example. I'm just like copying and pasting example. So they're going to say bleach is a solution of sodium hypochlorite. It's made by dissolving chlorine in aqueous sodium hydroxide, according to this chemical equation at the bottom. So they give you a huge chemical equation. Chlorine gas is basically mixed into an aqueous solution of sodium hydroxide. Okay, show using electronegativity values whether the following compounds are pure covalent, polar covalent, or ionic. What is pure covalent?
Pure covalent.
So the first one is sodium chloride. So which one is that? Is that ionic, pure covalent, or polar covalent? Pure covalent is basically means electronegativity is going to be less than 0.4. So it's basically pure covalent will be non-polar. Do you understand?
Yes, sir.
So it's either non-polar covalent, polar covalent, or ionic. So sodium chloride, is it, which one of the three is it? Is it non-polar? Is it polar covalent or ionic? So basically they want you to do the following. The difference in electronegativity equals the following. Chlorine is 3,0 minus sodium,
0.9.
which is 0,9. That gives me 2,1.
2.1.
But you saw that's a metal that's actually bonded to a non-metal, which makes it ionic.
But the ionic has to be over 2.1, so.
I know. But what you also must realize is those values are thumb sucked. Every textbook's got different intervals there. So in effect, if I look at my periodic table looks like this. Chlorine isn't 3,0. Chlorine is 3,16. Because this is quite unfair, right? And sodium is 0,93. So the difference there is 2, what? Is it 2,13? Sorry, I didn't make the calculation. I just guessed. Yeah, it's 2,23 actually, sorry. So can you see? This is your school periodic table. This is a proper periodic table that doesn't round off the values. So in the proper periodic table, I have 2,23. So that's why I'm saying those values are slightly rounded off. Do you understand? I know that you have the following in your textbook. Ionic is greater than 2,1. But because you've used rounded off values, you get a rounded off value. I didn't use rounded off values. I get 2,23. But anyway, that's a problem. So this is a bad question or a bad example because they should have looked at the textbook. But some of the textbooks just say greater than 2 or greater than 1,9. If anything is above 1,9, it's ionic.
Yeah.
Okay, so your textbooks say what? 2.1. That's a problem. Okay, and chlorine gas that you can see. Whoa. What is chlorine gas?
Like 3,0.
No. Chlorine gas, one chlorine, another chlorine. You can see the difference in electronegativity will be just 0. Why? It's the same atom. So that will just be pure covalent. No, or
Yes,
non-polar. Covalent, non-polar covalent, or pure covalent. The oxidation numbers you don't do. And then they want Lewis diagrams of NCl3. And then they want to know if the shape, identify the shape of the nitrogen trichloride molecule. So they have nitrogen with 3 chlorine atoms. And then the shape is what? Trigonal pyramidal. And then it's a AX3E molecule. And then they want bond angles and stuff. Bond angles might be in your textbook or not. I'm not sure. Okay, that's just the indication of what it looks like. So what I would suggest, start studying the work. And during the weekend, you are going to do some papers. You have to take the subject very serious. Otherwise, it's going to take you not very serious. The exam is not going to think
Yes, sir.
there's going to be a threat or it's going to be a problem, basically. Cool. I'll see you again sometime during the week. I think Friday or something.
Yes, sir.
Keep well. I'll put this on this channel.
Yes, sir.
Yes, sir.
Bye-bye.
Bye.
Okay. Bye.